Okay, hey. So, we've talked about computational modeling as a concept. We've talked about cognitive processes as a concept. Let's smush them together. In fact, that might be a recurring theme in this course. So, computational modeling of cognitive processes. If you don't know him yet, you should probably know about Phineas Gage. I come to fondly think of him as the guy what done gone and got his head blowed up real good. He was a railroad worker in the 1800s. He was working with a crew. He was tamping down some explosives to, do the work that explosives do, and they went off. The rod went straight through his head. He did not die. A shocker for the era. Maybe that's around the time when medical science had finally caught up to being able to keep blood in the body as opposed to letting it. So, fact is, he survives, right? And this is one of the first times ever in recorded knowledge that of a studied nature that somebody has had such an incredible brain trauma and lived to continue existing in the world. And he survived, but the thing that was fascinating about this scenario is that his personality changed in a pretty radical way. He was more rude and by all accounts, he was a very tame and mild person before all this, and he became extremely rude and blunt and aggressive and things like this. So he wasn't able to hold on a job any longer. Sad story, and he eventually becomes a sideshow attraction. And whatever, it makes sense to me. But the problem, the thing about this is that this is the first time that we're seeing such a macro level cognitive shift in someone with such a very clear and specific type of damage to the brain, right? You see over here, there's a specific hole that was pierced in his skull. It goes behind the eye, and up through the top of the skull. Now, this was not actually well studied. It was fascinating. It was important. It was actually really important for the field of understanding, neuroscience, psychology, cognitive science before it was even a thing. And it's this incredible account. It's this qualitative case study that is utterly invaluable because it creates this boom of, understanding brains, minds, and behavior, or at least seeking to. The issue, though, in this scenario is that there was never a single quantitative measurement of his behavior before or after the accident. I mean, not in any systematic way. We can infer categorically from hearsay and from people who knew him that his behavior seemed to have changed. But how exactly? They describe it, and it seems like there's some kind of overlap. He's shifted in his demeanor in a way that was surprising. But there's no real good records of the specific structures that were damaged because they didn't have fMRI. There's no, and so then we can't ask questions about why would any one structure of the brain cause this kind of behavior. So we have poor understanding of the damage, poor understanding of the behavioral change. And, there's the other question of what exactly was measurable here. Was he really totally more blunt and rude because of the specific damage to his brain? Or was it maybe because his job blew a hole through his head and now he lives with pain for the rest of his life? I'm not suggesting it's only one of those. I am suggesting the latter probably plays a role in his life. So, right. So this is awesome. I mean, it's an awesome piece of history. Not awesome for Phineas, but awesome in the true, awe sense. Wow. What a thing to occur that help us understand, oh crap, the brain is like parts. It's subsystems. There's processes involved. So this brings us to modeling cognitive phenomena in general. Because you think about the qualitative nature of the account of Phineas Gage, and it's fascinating, but it doesn't help really. All it suggests is that there might be differential structures somewhere in the brain. So, how do we, if we do want to understand what's going on, we can't just go around blowing holes in people's heads and seeing if their personalities change. Rather, what all the field started to shift towards was observing quantifiable things, right? And this brings us back to some of the math modeling. This is where we'll start. So if you have quantities, you have numerical quantities, that helps you address things like how much change, not just extant change, but how much change. It allows you to create averages, like we talked about. It lets you construct equations that can describe relationships between variables, right? So you can say, given, like a previous take when we were talking about weight, given a diet, given a height, given a population mean, predict a weight, right? So quantities are the next step up in complexity from just that thing happened, right? So what quantities are available to us, though? And the answer to that question changes over time. Things that we can observe that are related to someone's behavior, for example. The very first kind is like accuracy, right? How many of these questions can someone answer correctly? So things, this is like an eye test, right? You go to the eye test, they're like, hey, what letter is that? What letter is that? What letter is that? You get too many wrong, and they say, your vision might be compromised. Because the model is, if you can see a certain number of these things, that means your vision is okay to do things like drive, right? So that's the first, though. That's just sort of task performance measures. We also can start to do things like measuring time, right? So when stopwatches become clearly and easily available, and nowadays they're available on your phone, right? Right, any program can do stopwatch behavior in one line of code, essentially. So, but this was kind of a revolution once upon a time. How many people had their own pocket watches to start and stop time with? But the trick is that once you're able to record things like reaction time and response times, that adds another dimension to the picture you're painting of somebody's behavior, right? I can track when and how often things happen. I can track you got everything right, but it took you 2 minutes, versus somebody who is more in a healthy brain might only take 10 to 15 seconds, right? You see the differences. Keep adding more technology. We get an eye tracker in there. You can start tracking eye movements and pupil dilation amounts. Get heart rate monitors, get skin conductance. Is the hair, are your hackles raising, right? fMRI, you get bold responses to understand where blood is flowing in the brain, implying activity. EEG, you can get the brainwave stuff, the spectral decompositions. You can get event-related potentiation. So something happens and you see a spike. You got to do that about 1,000 times to get any real data. But the fact is, there are tons of things we can use to measure behavior, measure phenomena, right? And all of these measurements are some kind of reduction of the actual phenomenon. If I have, for example, all of your inputs on a video game you played, I can recreate your behavior in that game. But that behavior it's a capture of your behavior, but it doesn't really capture everything inside. It doesn't capture all of your behavior internally. It doesn't capture anything else about the reality of when you played that game. It just kind of captures extant actions that were taken in a particular order. So they're a reduction, we're not measuring the actual processes, but we're measuring some artifact of those processes, something that was the result of those processes. And we can use measurements to make predictions about these cognitive processes. We'll talk about why there is more to the picture than that, but let's get into some of these ideas. Oh, and first we need to talk about also measurable is not just things related to behavior, cognitive behavior, but also things like your demographic information, right? So grounding this, we need to model things that will be somehow useful, right? And the kind of the point of modeling is make predictions, explore, etc. So we're not just going to capture behavior traces and then not tie them to anything else. We want to tie them to other things like age, sex, education level, economic status, right? Medical information. So, when you're applying medical models, you want to have a lot of information about, like, are they on certain medications? If your blood pressure is high, but you're on a medication, then maybe don't apply more blood pressure medication. Interesting. So, yeah. So these are the kinds of measurements we can make. Let's talk about let's sketch a world where we are modeling Alzheimer's for the first time. So it would be great if we could predict Alzheimer's disease incidences. We're better and better able to every year, right? But it's still not something that we have nailed down. It still often comes as a surprise, and a grim one. So the science isn't yet, precise or settled on the precise causes, right? We don't know everything about Alzheimer's, but we have a lot of data. And with that kind of data, with data about observations of Alzheimer's patients, we can create mathematical models that help us predict whether or not someone is likely to get it. For example, we have lots of information showing that obviously it's more common in elders, and it's more common in people with family history. Couple of things, right? We don't know the precise genetic markers that cause this, although it's heavily active research. Obviously, this is all based on sort of a broad view. I'm sure there's tons of huge advances every day. If you know about them, tell me. Right. We've also developed certain cognitive tests that help predict Alzheimer's as well, which was done by having people with and without this disease try and do tasks and then sort of figure out which ones were helpful in differentiating the population, right? The mini mental state exam is the one used. And right, so let's sketch a model that will be useful for predicting Alzheimer's. The relatively simple version is the probability of Alzheimer's, so some percentage is what we're trying to get on the output, would be equal to age times some value A, so their actual age, like what in years, how old are they, some index of their family history and times some constant B. So the family history would be like some value associated with, their how many relatives or something. How many relatives have had it diagnosed, right? And then MMSE performance, so whatever their score is on that test, right? So you have these three numbers. You have their age, you have some quantification of their family history, and you have their performance on this test. And then you have the intercept coefficient, which is most likely related to the mean. A, B, C, and D in this case are these multiplicative coefficients that sort of give the weight. How important is age in predicting Alzheimer's? How important is family history? How important is the MMSE performance, right? And those are all determined by the data. That's what the statistical modeling is. That's what you're doing when you make a linear model in a stats course. You are creating this weighted evaluation of, hey, here are the numbers I'm able to measure. Can you help me predict the next one? The one that's really important to the patient? So to use this model, you plug in the person's information and it'll give you some estimate of their likelihood of having Alzheimer's. Hopefully you're building your models about the future, right? So probability of having Alzheimer's in 10 years, not today. That's a bad shot. And just like that, we have taken this mathematical model and created, we've used the observable data, we've done the stats, we made the equation, and we are making helpful predictions about somebody's health. Nice. But there's limitations here, right? So we should be proud of the ability to help predict whether or not someone's going to develop Alzheimer's in certain time frames. That's an important thing that we have down, not totally ironclad, but we've been working on, and it's working. It's helping, because the earlier you get to Alzheimer's, the easier it is to treat it. Sorry, aside on Alzheimer's, it's a real bad disease. So, coffee sip. This is useful, right? Especially in medical scenarios. But also, I want to remind you that this was a sketch. There's much better actual models in reality, and the MMSE probably includes a lot of the values. But this is us sort of doing the common sense distant looking, sketch of it. So, okay, this is interesting because it's only really given us a correlation, though. Now, I'm sure you've heard of correlation and causation. There's important differences there. What we get in the correlation is these numbers trend together. We don't get what caused this disease. How does it function? How does it play out over time? What specifically starts to degrade? What kinds of degradation patterns are predictive of this versus some other kind of disease? What are the mechanisms of Alzheimer's, right? So we found this useful relationships in the data, but we haven't learned anything about the underlying process when we do this broad scale, mathematical diagnostic type statistic prediction. And this is like sort of the major issue with Alzheimer's research. It's really hard to figure all this stuff out. So we still struggle to treat the disease because we don't know all of the things that it is arising from at the lower levels, right? So, okay. Alzheimer's case is this scenario where we're making progress on something that is very useful in an applied medical scenario. Now, I want to keep zooming in. We're gonna push math modeling as far as we can to understand process. So you can still get some information about a process as long as you are able to zoom in a bit more, right? So we can zoom in and try and capture relevant behavior that's not maybe at the whole person level or maybe the multiple decades person level, right? But more at the seconds. What happens to behavior over seconds around something useful like memory decay? Now we'll get into this more later in the future, but for now, here's a sort of another sketch, right? The phenomenon is humans forget stuff, but the question is how quickly do we forget stuff? This is just a fact, right? We forget things, but it probably won't come as a shock to you that you forget things more the longer it's been, right? So the experiment would be, right? There's many of these out there. So have people memorize a list of words in a laboratory, wait certain amounts of time, different amounts of time, and then have them try to reproduce the list from memory. Sounds painfully simple. It is. Working in a COG psych research lab, you do a lot of list memorization stuff. It can be painfully simple. But what you're doing is you're collecting data. You're collecting data points on their performance on the task with different time intervals, right? You're varying how long they have. And then you're saying, now try, it's been 10 minutes. It's been 6 hours. It's been 6 months sometimes, right? So you get your data, you get enough people contributing their data to your data set, and you do your stats. And the stats is this whole fitting process, right? You run different kinds of linear models and different transformations and different equation types, and you get one on the output end that fits best. And in this case, the one that fits best in these scenarios is this exponential model, which is some memory strength, which is sort of an arbitrary number. Just think of it as a percent score, right? So your percent score on the memory test is going to be whatever your initial learning was, usually 100%, but sometimes less, times the decay rate to the timeth power. What do I mean by timeth power? Decay rate caret time means you're taking it to the exponent. And the decay rate is something like 0.9, meaning after some amount of time, in this case days is the simple example here, your initial strength goes down by, looks like 50% per day, right? Now this is not exact. Memory curves are different from different scenarios, but you're seeing the pattern, right? So every day, your memory of the list will decay a bit. Decay more, decay more. Now it's not dropping 50% the first day and then the rest of the 50% the next day. It's dropping 50% times half of that, which would be a quarter, then an eighth, and it decays slowly. Usually doesn't ever fully extinguish, but it can kind of become pointless to recover. So that's the model. right? Here we go. Once again, we've done math modeling, and we've come up with a useful equation for estimating how long it takes someone to forget an arbitrary piece of information. You know the limitations are coming. So this time we did capture a bit of process to this memory decay. We can make these fine-tuned predictions using this, right? We can say, oh, it's been 6 days. I bet they'll perform 70%, 10%, whatever the values are of your actual model. But the model comes from this very constrained study, uses very clean lists of arbitrary words. None of it's like meaningful to your life, and none of it's really going to get interfered with. That's at least that is the goal of these kinds of studies. You got to do it clean. It also doesn't examine anything that actually happens, so they don't account for, oh yeah, I got no sleep last night, or oh yeah, I haven't been able to eat this week. You know how students are. That's another issue with this. That's all teenage students. So, point being, they can't just shut their brain off. they exist in the world between observations, right? The processes are still occurring, even as memory decays in this great way. It's great that we have the math model, and it's great that we have it predicting a specific kind of memory, but in the real world, that's not really helpful necessarily, because the real world is full of other information. Okay, I paused. Just starting back at the start of this slide. So we sketched all these models so far, right? These math models, finding these useful relationships between measured variables of real complex phenomena in the world, but just features of them, pieces, mathematical bits of observation about them that help us make predictions about possible outcomes, right? But these things don't really help us understand what's going on between the measurements. We saw flickers of that in the memory model. You start to get there, but it's hard to continue to drill down far enough to just measure those things continuously. So a different approach is you have to treat the phenomenon as a process that you are going to model, not just an equation, right? So when these things are when you model as a process, when you do this sort of computational modeling, you're acknowledging that these things are extended in time, not just a single data point. There's closer attention paid to mechanisms, right? So what specifically is causing the brain to break down in Alzheimer's or in memory? What is causing memory decay? What is causing the pattern of whatever thing you memorized to sort of become less and less accessible over time? Why? Why does that happen, right? And it also treats them as dynamic, right? As the phenomenon themselves and the environment are actually doing things, they're interacting. You can't break away from that. In these models, they sort of account for that, right? Or they attempt to. So when you approach modeling as modeling a process step by step, we're committing to this view of the process that has, it has to at least function similar to the thing that we're trying to model, and it will contain some ideas about how. So let's step towards a computational model. One of the earliest models that you might consider computational is Miller's magic number 7. Now, have you heard of that one? Probably at some point, but here's the deal. So George Miller, in 1956, came to the conclusion that humans can only remember about 7 items. What does he mean by that? In short-term memory, give or take 2, depending. And this was certainly based on observed data. He did studies, and it began these statistical findings from several experiments aimed at figuring out, okay, well, how much can people kind of keep juggling in their mind, in their mental set, right? And the findings were, people hold on to about 7 items. This is where you could just stop with the math and say, okay, that's good. But still, the questions remain of why? How? How is this proposing that the brain is arranged so that this could be possible? It's great to have the empirical observations and build, your statistical models around this, but what else, And short of, an incredible leap in technology, which is probably coming, honestly, but short of that, we need to take a different approach to try and shed light onto these processes. So here's where the computational model begins to emerge. Miller went beyond just the observed relationships, right? Started explaining the phenomenon with a model of the structure of memory. So here's the short version. Well, we can touch the figure in a minute. The memories themselves are considered chunks, just like blobs of information that move together in the brain, or at least help keep each other active. It's not literally just one number or just one name or just one phone number. It's sort of a squishy concept, but things that tend to group together, right? If I asked you to remember your phone number, that's a different effort. That's sort of, they're all connected, right? When you recite your phone number. But if I ask you to remember the number 10 for 5 minutes, that's a little bit, you have to put more, that's less useful. You haven't encoded that into a chunk. It's just going to be 10. Oh, I got to keep 10, a single value. So the memories themselves are conceived of as chunks, and chunks come in as input to working memory. They can either come from the outside world, or they can come from long-term memory, like something that I remember from my past. But either way, chunks all kind of meet in working memory. This is where the titular 7 items comes from. That's how many things we can keep in working memory. Information can also be stored and retrieved, like I said, in long-term memory and come back to working memory later. So to test this model, it's not just plug in values. It would be something along the lines of, so you can do it sort of on paper, right? This was a bit before we started to have computation available cheaply to everyone. So you could input a list of words one at a time, one word at a time, and we were considering them a chunk. And you would have them enter sensory memory, and you simulate, half a second. And then you send, that goes into working memory, and now you add another word, which goes into working memory, add another word, and the capacity of this system is now defined by some behavior that happens over time, not just some snapshot of observed math, right? This is, the early steps of computational modeling, but it is a process as opposed to a number. And here's an important idea. Computational models, with these, the structure is the theory, right? So when you construct a computational cognitive model, the structures you build into it are assumptions about the nature of the underlying processes, which are then taken together, become the theory of what you're proposing, right? So in this model, they say there's some way that memory exists sort of close to the senses. There's some working memory that you are actively using, and there is some long-term memory that is sort of the everything else that's stored forever from your memory of childhood or whatever. Some things can be forgotten, but things can be kept maintained in working memory through a process, right? There is nothing originally at the time of this. They didn't have any evidence that suggested all these things were exactly how it worked, except for some small amounts of findings. So what they're doing is they're adding new wrinkles to the model, or adding new specific details to the model. It's not just saying you're probably only going to hang on to 7 values. It's saying here's how and why I think some values will fall off and some will stay active, especially through this rehearsal bit, which we didn't really talk about. We'll talk about memory again, don't you worry. So we're seeing in the Miller model this step away from just these observed relationships that are largely correlative, not exclusively, but largely, and toward a model that begins to explain the process of memory, right? Where we are, what happens surrounding those observed bits of memory decay. It isn't very robust, right? It represents the early steps, right? So these days we've gotten much more complex with our modeling techniques, but this is the first time you're seeing movement. And okay, obviously every time I'm the very first, No one can say that. But they're the first time in sort of a broad sense in the literature of this field. So the cool thing about this to me, like just as a curious researcher minded person, these things open up the door to tons of questions that you can ask now. You say, okay, cool. You think this is how it works? Then what exactly is a chunk? Do chunks have limits on size? Do chunks have any other properties that we need to study? Is it always 7? What about working memory would cause it to be only 7? How do we explain people who memorize 1,000 digits of pi? Or like that historical guy who could like memorize hundreds of names at every banquet, whatever. And then also, is there a biological basis for this model, right? These arrows and boxes look nice, but is that how it could exist in the brain? Potentially. But how? And these give us new guiding questions, right? Searching for the processes is how we have made so much of the progress that we have in this realm. So, another thought about all this is that as we step further and further into computational models, we see that computation power continues to evolve. And that means that our models will get more and more robust. I mean, have you seen a video game lately, as my example here? There's this deep discussion to be had about games themselves as sort of like rich computational models of certain things. We can talk about it some other time. Maybe I'll make a little bonus lecture on it. But like more directly, if the goal is to break phenomena down into interconnected subcomponents that have their own sort of rules and features, there's never been a better set of tech, right? We have modern computers have massive distributed processors in their graphics cards. So they can compute things in parallel. Same with the CPUs. We have effectively limitless storage capacity for most of the types of data that we would be talking about in a cognitive sense. And you can run thousands of simulations simultaneously on a billion computer, like you can do a lot of variations on the models and they don't ever get tired. You can simulate all night and get something back. So, and again, to highlight, this is all tech, your phone in your pocket has most of these properties. You could do a lot of cool stuff if you had root access to your phone and could use, developer tools on it. So the point is, we've begun on the trail of cognitive models, but now we're trying to, it's important to keep in mind that this is just the beginning in terms of what we talked about, because the approaches get more and more complex, more and more powerful, and they start to diverge a little bit from just modeling cognition to taking these interesting tools we've made to model cognition and sprinting away with them. This is an important concept. This is a pre-2020 prediction from IBM about, it's based on Moore's law. I forgot to put that on the slide. I'll put it on before it becomes notes. Moore's law says that the amount of knowledge / technology, we equate them in these scenarios, doubles in increasingly shorter time frames. So the amount of knowledge doubling rate in 1440, it took about 400 years for cultural, group, global, societal, whatever you want to call this, knowledge, consensus knowledge, to double. Then it was 50 years in 1900. Then it was 20 years. Then it was 10. Now in 1980, it was about 8 years between knowledge doublings. In 2017, in terms of both, again, knowledge and tech, it was every 13 months. So, I mean, think about it. The internet has become. Computation has exploded. They were predicting in 2017 that by 2020, the doubling of knowledge on Earth would be doubling every 12 hours. The power of exponents can never be understated. Make sure you understand exponents. That's exactly the same problem with was the same problem with COVID. That's the problem with AI right now. People are not thinking exponentially. They're thinking, oh, this is going to be a problem in a year. Like, a year. Optimism you have. So stuff is changing rapidly. And that means that things are exploding in terms of the capacity to compute, which means that the models have more and more room to play. So this is not meant to be a scaremongering tech. It's just an important framing device. Used to be that you would, in 1950, it would take 20 years for things to change substantially. These days, it takes a week sometimes, especially given all the AI. So, okay. Finally, well, not totally finally, but this brings us to a discussion, right, on where the latter half of this course will touch on more, and it's the idea that on top of modeling human cognition for the sake of medical advances and scientific inquiry and understanding ourselves and our brains and everything good like that, we also kind of accidentally end up building new general purpose tools, right? Modeling expert decision-making patterns leads us to being able to capture that kind of decision-making in decision trees. That's like, they have tools now that can help, especially in like nations that don't have access to round-the-clock doctors. They have tools that will help you start a medical diagnosis based on the same data that a doctor would be using to make those decisions. Like a tree that says, oh, how's their heart rate? Well, okay, it's safe here, so disregard this half of the tree. You keep navigating down the tree in a process. So useful things like that. Modeling neurological information processes led to neural networks, right? Seeing how one unit responsible for basically a single bit of information joined together in mass quantity. Here we are. And then to things like modeling human language processes gets us into transformer models, most famously our current bud, GPT. So, yeah, let's recap and get out of this one. Computational modeling computational modeling of cognitive processes. We took a walk through the history of sort of understanding cognition in many, many ways using models, right? Phineas Gage was an anecdote that was never fully studied. Then we start into math models with observable data, making predictions about cognitive phenomena. And then as time and tech move forward, we gain this ability to simulate possible structures and processes going on inside the mind. And it's really exploding still. So ain't slowing down. And a reminder, I will keep peppering this throughout the whole course. Models are always wrong. They are still wrong. No matter how cool or interesting the model becomes, it is still wrong because it is a reduction. But we are quite scrappy. We find ways to use them, make inferences about them, improve them, make them useful, right? And that's one of the core principles. Okay, and that's it for now. Take care.